Okay? So that's one way to do this. But it also means that this is now delayed. Your normal command is delayed. But this is doing you're really doing your command tracking, right? So really look at your system and what the feed forward does. For instance, I don't know if you've tried it on the Tustin, because the Tustin is very easy to do the inverse of. This here would be the command feed forward for the Tustin, right? And now that's what I meant when I talked about. Oh, I should get a camera over there. And I talked last time about manipulated, that you see, if you do something incorrectly and put your pulse into the left plane, you see forced oscillation, and not on your state, but on your manipulated input. And that's basically what I'm talking about. This here has a pole at -1, right? That's forced oscillation. So this feed forward might work because it's physically possible, also because you saw the current in the Tustin changes right away. In real world it doesn't. But if we had this kind of a plant, which it isn't, but if we had, we could do this feed forward, no problem. And let's see what happens if I use this feed forward now. And this is just what the Tustin thinks what it is. It's not physical, and we see that on the actual system it won't look this nice. But if it was what it thinks it is, we see that we can also make the Tustin perfectly track this. But what does the manipulated input look like? And that's what I meant by look at your NSDOC. This has a pole at -1, so we have forced oscillation, but not on your state. It's not on your state, it's on your manipulated input, because in your state, it actually cancels, right? But your manipulated input does this now. It basically gives full voltage, no voltage, full voltage, no voltage. And a mean, it actually means it has the correct current. And you see that the amplitude is getting bigger because we demand for more current. But this is not a good solution. It is dynamically really fast and it looks nice if the system was like this. But this is also not something you want. If your voltage or whatever your manipulated input is changing with full amplitude minus and plus, you probably get some issues in your system. EMD or whatever problems, right? It's probably not a good idea to design it this way. But it looks from the state, it looks pretty good. Now let's look what does it do really on your system. So that's what it thinks it is. Now if we put that kind of feed forward on our real system, oh, we do. I didn't put it there. You have to activate it. It's up here. So if we put it now on the real system, what do you think what will happen? So it obviously won't do what it thinks what it does, right? That's what the real state is doing now. Because the pole didn't cancel, so we still have the forced oscillation in there. So really bad behavior. Always think about what your NSDOC is doing. Look at the equation of the NSDOC itself. Is it physical? Is it okay? Does it have any poles that could be problematic? And look at the signals that are important. So the manipulated input should be okay, and also your state. Right? So NSDOC, or the feed forward, can be a problem because it's based on an inverse solution. But there's usually a way to get around it. For instance, what I did with the Z to the -1 can be a way to get around it. There are also other ways to get around it. For instance, a state filter. And we're really running out of time, but what else do I want to talk about? Oh, DID. Okay, maybe we do DID first. Okay, the final thing we need for our control is disturbance input decoupling. and we haven't yet talked about it. Did you try maybe purposely didn't put any voltage into our system in homework 3, right? You didn't have grid voltage? Did you still include it? I don't know, but on the homework sheet I explicitly put the disturbance out. Because there is some issue with disturbances, or DID. Because technically if we want to decouple the disturbance, we need a continuous signal, right? The actual disturbance is a continuous signal, so if we don't want any influence of it, we also need a continuous signal technically. And that we cannot do. There's no inverse of the latch. You can't just make a continuous signal. We just don't have the interface. Okay, so I'll do the best explanation of this. So this is the actual disturbance, and we try to basically make these two that they cancel one another, right? And this cannot be perfect because of the problem that we're in this group, right? So we try to basically make the influence on our state 0. So we hope that the Z transformation of the disturbance signal times this, and I made this in a very general case, and we also have something here and here. In our case, this would be most of the time as well. Right, we try to do this. We hope that this signal times this, so the influence of the state, minus the sampled version of this, times DID times the whole NSD of Z, cancel one another. So that this state does not see this influence. And that really is not possible. You can get close. And the real problem is that there is no inverse of this. We cannot cancel the latch effect. So what we very commonly assume is a latch assumption. We assume that here's a latch also. It's not true, obviously not true, right? But it's the closest we can do. So if our sampling time is fast enough so that the latch approximation is true, or that is close to reality, then we can actually make this happen. Because then, in this case, what would this be? In general, from this map, we hope that GPID equals Z less GP2 S over S. That's what we try our transfer function for disturbance and group decoupling to look like. And if this is, for instance, just a gain, it will turn out that GDID will be 1 over the gain. And then that's okay. But you always have to look at what will my GDID become, because it also is again inverse of NSDOC. So usually we hope that this basically that the influence cancels with one another, right? Because if GP is basically, or legend GP is basically NSDOC, for instance, if this is just a gain, then these two are basically the same except of the gain. Then all of the inverse stuff cancels out. But if here's still something that doesn't cancel out, that's a function of Z, then maybe we still have, again, issues with the inverse, right? So really look at what your GDID is. And if you have issues, then you have to maybe go state back, try to make it cancel somewhere else. But always look at, is it physical, what you're trying to do? Otherwise it won't work. You don't have these issues quite they're not quite the same as a continuous, but the ideas are the same. Okay? But you have to look at your transfer function to use it. Okay, so we actually through with the 2 hours now. So if any questions on this, we can still talk about it. We can play around with the model and basically homework 3 if you want to. I should also give you homework 4 that you can look at it if you have questions.
In the same way, we can't cancel the R component and I component also exactly, right?
Did you try it? It's actually, it's a little bit surprising what happens if you try to do it. So you think it doesn't work, right? So if you look at the differential equation and you see this e to the minus t over tau, it seems like you cannot decouple out, right? So I would have thought the same. And the interesting portion is if you look at these approximations, you still see the R, and then, so that's why I think it's not totally 100%. So let's try to get the wording right. So I think the approximation models are sometimes helpful to still, and also the continuous approach to come up with a cool solution. Because if you try to do the decoupling with the actual direct discrete model, something interesting happens. And let's do this now that you talked about it. So what will happen is you get NSD of Z over 1 minus NSD of Z times R hat, right?
Yeah.
This is what we do. So that means you get 1 over R times 1 minus e to the minus t over tau to z to the minus 1 over, and I already multiplied the 1 over down here, it would be 1 minus e to the minus t over tau z to the minus 1 plus R hat over R, and 1 minus e to the minus t over tau z to the minus 1.
No, 1 second. These things, this is including the R also, right? That transfer function which we have.
Yes, it's in the tau. And there's 1 over R, and that's why it's here. So, and if you look at this, it's kind of interesting if you put all of these together. What happens is, that this transfer function becomes this. And if you look at this, if R is close to, or R estimation is close to R, this is 0, and this whole thing becomes this. So with the difference between R and R, you move the eigenvalue closer to +1. So you actually do something interesting with this. If you have this correct, it actually looks even closer to the rectangular version. Right? Because the pole gets to +1. Before you had the poles here and here, this was the one, or for the open loop, you only have 2, right? That's your e to the minus t over tau. And with the resistance, what you do, you actually move it to +1. And if you then include your controller, you have 2 poles now here. And that's how the rectangular one looks like. So you actually make it more look like 10-way accumulation. It's kind of interesting. It actually does something that might be helpful, because you move your eigenvalues to something defined now, and it doesn't depend really on t anymore. The eigenvalue doesn't.
Yeah.
Right? So, it can be something good. Depends. Depends on your system, depends on what you're trying to do, depends on where you want your poles. Maybe it winds up to be an interesting idea. And it came basically from continuous thinking and from approximation model thinking, because in the NSD of Z it's really hard to see that this will happen. So it can still give you some cool ideas, but it's really different. It's really something different than decoupling our continuous method. In the end, it looks kind of just like an integrator, right? Which it would also do with continuous method.
From that equation to this, from that ratio to this ratio, we have used some approximation.
Sorry?
Have you used any approximation to get this relation from the first one?
So this is the actual list. The NSD of Z is, what do you mean? This is the same, or what are you saying?
Okay. I got it.
Okay, I just used Mason's rule with the new R. And the original one was basically this, and I multiplied it down, and it winds up. I probably did the math a little bit too quickly. But that's the new pole. It's now pretty close to 1, and if you are approximating, and it depends on your approximation of your R. If it's perfect, you actually have pure integrated or an integrated pole.
Yeah.
So it actually sort of does what you do in the continuous domain as well. And it's hard to see because it's one kind of function. You're welcome. So another trick to do feed forward, by the way, is what we call a state filter. The state filter helps us to create already trajectories that are feasible. So for instance, imagine I want to give you already the answer for the homework. This would be the bonus. Let's do this. So if your plant basically looks like a time weighted accumulation, right? So t is e to the minus 1 over 1 minus e to the minus 1. You could build something that looks like an open loop observer, but we call it a state filter. An observer sort of looks like a state filter. And you could build like a PI control or anything on this to give it a bandwidth. You could also just do it just a T control. And then you have your time weighted accumulation. So times T. And another way to write time weighted accumulation is also this. Right? This is also 1 over the 0 minus 1 over 0 minus 1. And this could be now your output. That's your output star. That's the actual output, or input to your system, whatever you want to. Close the loop, give it a bandwidth. And if this is your actual plant, and you have the actual plant in here, you now have an O star. You could also have an O star k plus 1. And back here, that could be the reference for the manipulated input, for instance, right? This would be, for instance, the force. So you also have already the feed forward for the force. And all of these would make sense with one another. Because this will be consistent with this, right? And this will be consistent with this input, because it already looks like your actual system. So if we make this being tracked with it, with a certain bandwidth, you already create trajectories for all your commands. And you can use these as feedforward. Also another way. If you do the math, you will see that this times this whole, if you take it from here, it's basically inverse of this already, right? And you did the inverse without using z. So you can basically just put it on top, and there already is the inverse. But it's the inverse of this new reference. It's not using this. Okay? But it uses an original command. And this already creates you all the references for your system. And we call this a state filter. I put it in a bonus task on homework 4, where this could help you to build all the state references for your system. Because they are consistent with one another. And you shouldn't get any issues with unfeasible commands. Yeah, sure. Okay, so what this is, it's basically a model of the system, right? And we already control it with something. So it sort of looks like an observer, or call it what you want, but since there's a feed forward, we literally just, on our own model, the model track a reference. And we can make this super fast or whatever we want to, what the real life behavior should be. But that also means that all these signals here are physically possible, right? So if this has a certain form now, then the force is the correlating force that yields this. So it cannot be unfeasible anymore. You could also put your limits here, right? If you put a limit on force here that you want in real life, then this force can never exceed that limit, which also means that this is still